Okay, this is Giancoli Physics, AP Edition, 7th edition. We're in Chapter 10, Fluids, and we're working on problem 41 today, so let's go and jump into it. That problem reads, a 12 centimeter radius air duct is used to replenish the air of a room 8.2 meters by 5 meters by 3.5 meters every 12 minutes. How fast does the air flow in the duct? So go ahead and pause the video, take a few minutes to wrap your brain around that, and you have a plan coming back and see how our notes compare. Okay, as with most problems, it's a good idea to go through and identify the values you have. We have a 12 centimeter radius air duct here. As far as I know, that's the only radius we have, so let's label it R with no subscript. We have three linear dimensions here, which can effectively be used to calculate the volume of the room. We use capital V for that. And we have a time here that's being done in. And then the question being asked is, how fast does air flow in the duct? So you might think that would be little v, velocity, which seems reasonable. Now this is a level 1 problem. In theory, this should be an easy plug and chug type of problem. But you're going to find there's really no equation set up for this already. It is related to an equation. This is where your sensitivity to dimensional analysis will come in handy. As you may have learned from previous problems or previous discussions, if you understand dimensional analysis, you can invent or at least verify a lot of the equations you use. And this is a good example. Again, level 1 problem, but not actually a plug and chug. So let's take a look at this. If you're going to replace the air of this room every 12 minutes, that's this volume every 12 minutes. That's a volume per time, also known as a volumetric flow rate. Depending on your textbook, they may indicate this as a V dot, the dot indicating rate of change. That's a volumetric flow rate. How much volume per time? Now this is where it is related to one of your other equations that you do have. If you look at your fluids equations, your list may look a little different depending on your textbook. But we have this continuity equation here, which is essentially a conservation of mass equation. This represents the amount of mass flowing into a region. This is the amount of mass flowing out of the region. And unless you're stockpiling or bleeding off mass in an area, what goes in has to come out, is basically what that's saying. It's a version of conservation of mass. But you'll notice that's an area times a velocity. The velocity is a length per time. So imagine you got a cross-sectional area. You got a cross-sectional area of pipe. And you had a certain length passing through that area per time. That would represent a volume. If it's going there through there per time, that would be a volumetric flow rate, which is what this is representing. So area times a velocity is the same thing as a volume per time. Again, it's dimensional analysis. So even though we're not really using this equation, we are using the concept where the volumetric flow rate is the area times the velocity, which is what they asked us for. Now, you may remember my penmanship is not the greatest, so we have to be careful with our V's here. We have a capital V and a little v. I'll try to put wings on it or make it small. So that's volume per time equals area times velocity. Now, we have an equation to calculate volume. We've got a time here. Area we can calculate using a radius of an air duct. We assume that means it's circular. We can use that radius here, and we calculate the velocity. So we have everything we need here with some potential unit conversions, but we're looking for the velocity, so we'll just rearrange that equation. Little v is going to be your volume over area times time. Now, area itself for a circle is going to be pi r squared, so we can insert that. And because everything here is in meters, that's in centimeters, we're looking for a velocity. I'm going to go ahead and convert everything to meters and seconds as we go. That way we don't have to do the unit conversions intentionally later. So a volume is going to be the 3 linear dimensions for our room, the air that we're replacing. That's 8.2 meters times the 5 meters times the 3.5 meters. I'm going to divide that all by the area, which can be pi radius squared. Radius in this case is 0.12 meters. Go ahead and convert that on the fly there. That is squared. And multiply by the time. That's 12 minutes. 60 seconds worth of 12 minutes is going to give you 720 seconds. Again, if you're not comfortable with those conversions on the fly, you can do them more deliberately and formally. But I'm pretty comfortable with those. So we can calculate our velocity using those numbers. Now, as always, before we pick up our calculators, we should do some mental math here. 12 squared is 144, but with the decimal there, that's going to make that about 0.014 times the 720. If you figure that 720 is about 15% shy of 1,000, we can make that 0.014 and that 720. That works out to about 10. Times pi is going to give you about 30 down here in the bottom. 35 divided by 30 is about a tenth. 5 times 8 is 40. So a tenth of that should be about 4. Let's go ahead and pick up our calculators, crunch those numbers, and see if we get what we expect. Okay, after crunching those numbers, my calculators tell me about 4.406. And notice we have cubic meters in the top here, square meters in the bottom with seconds. That's going to end up with meters per second, which is what we expected. That checks roughly with our mental math. And 4.4 meters per second is reasonable for a flow rate in an air duct. With the significant figures we're working with, we'll round everything to 2 significant figures. That's going to be about 4.4 meters per second. That takes care of that one. We're on to the next.